Hey everyone and welcome back. Today we're going to be continuing our exploration of systems of differential equations and focus on a particular type of system known as a linear time-varying system of differential equations. So let's look at the type of equation system that we've been looking at so far and the structure that we know how to solve already. Let's assume that we have two functions for simplicity, x, which is going to be a function of some parameter t, and let's assume it's a linear differential equation in two variables. In particular, let's assume it's constant coefficient as well, so a11x plus a12y. And let's assume that we can allow for some inhomogeneous term. Let's call it, for example, f1 of t. And let's look at y prime of t to be equal to a21 of x plus a22 of y plus another inhomogeneous function f2 of t. So, as we already know, we can write this in matrix differential form as the derivative with respect to t of the vector function x of t, y of t, which I'm just going to call xy just to keep things short. And this is just going to be equal to a11, a12, a21, a22 times the vector xy, and that's going to be equal to f1, f2 on the right-hand side, or you can just add it and call that your inhomogeneous equation. So we already know the structure of this type of differential system. In particular, we're going to be looking for a general solution that's going to be equal to xy homogeneous plus xy particular. Here, this homogeneous function is related to the eigenvalues and eigenvectors of the matrix A, where A is this constant coefficient matrix. This is going to be our x. This is again our what I'm going to call x prime. Let's assume that's a vector as well, and let's call this a vector divide function f as well. Right. So the solution for this practically depends solely on these coefficients, but notice that this is a constant matrix for all time t. So since it's a constant coefficient matrix, and the solution of this differential equation depends entirely on the eigenvalues and eigenvectors, that means the dynamics of this system of differential equations remains constant as well. But if instead these are now functions of time instead of constants, that means the eigenvalues and eigenvectors will also be functions of time, and hence the dynamics of the system will potentially be time varying. So that's practically what our focus is going to be today. So question, what if A is a time varying matrix? That is, A is a function of time. Right? So again, if A is a function of time, that means the eigenvalues and eigenvectors will also be a function of time. So we can say that lambda is equal to a function of time, and V is also going to be a function of time, where lambda and V are associated eigenvalue and eigenvectors for this particular potentially m by n matrix. So let's assume that we have our general differential equation system, x prime of t, which is going to be an m by 1 vector divide function, and then we're going to have a of t, which is going to be an m by m matrix, and then we have our x of t, which is going to be like our xy from before, which is again an m by 1, and then we have our f of t, that's our inhomogeneous term, which could be 0 for simplicity, but generally speaking that's still going to be an m plus 1. So this is what we're going to try and solve today, or at least understand in most cases. So what we're going to do is we're going to define our matrix of independent solutions, and I'm going to call this capital Phi of t, and this is going to contain x11 of t, x21 of t, all the way down to xm1 of t, and then this is going to continue all the way down to xm1 of t, xm2 of t, all the way down to xmm of t. So what we have here inside of this is practically the Wronskian, or at least the matrix that generates the Wronskian, right? So these components are our m independent solutions. So in our previous case, it's like x1, y1, and x2, y2. So if they are indeed independent, that means the Wronskian, which is again a function of time, which is going to be determined or defined as the determinant of phi of t. This is going to not be equal to 0 for all time t, let's assume in the set of real numbers, because we're assuming that they are independent vectors of time, right? And in particular, they're not constant vectors, but they're time-varying vectors, right? So if that is the case, and if this is our fundamental system of solutions to our first order m equation system of differential equations, then, and actually let's assume that this is the fundamental system of solutions for our homogeneous system, right? Because the general solution for the inhomogeneous is just our homogeneous, which is going to be for our 5T matrix, together with some particular solution, which we can usually find by like variation of parameters, power series, or potentially guessing. So if it's a solution to our homogeneous equation, that means phi prime of t is just going to be equal to a of t times phi of t, because it's a solution to our differential equation, which was x prime of t is equal to a of t times x of t plus 0, right? And here 0 is a vector, not a number. So if that is true, and let's assume that the determinant of this is non-zero for all time, which we're assuming because we're assuming that these vectors are independent. That means the inverse of this matrix exists and is unique for all time. So we can multiply both sides of this equation on the right by phi inverse of t. So we're going to get that a of t is equal to phi prime of t times the matrix phi inverse of t. And that's what we have, right? And it's very, very important to note that this is not necessarily equal to phi inverse of t times phi derivative of t, because keep in mind these are matrices, and matrices do not necessarily commute under matrix multiplication. Right? So what we have here is an equation that relates our solutions, which are located in phi, the derivative of them, and the inverse of that matrix that contains our solutions, and that uniquely represents A. Right? So that means A of t is uniquely determined by our fundamental system of solutions. Right? Now, we haven't really talked about how to find this matrix phi, which is going to contain all of our solutions. But if we do know what our solutions are, without even being given a differential equation system, we can actually uniquely determine which system of differential equations these solutions correspond to. So let's actually look at an example of sort of how that goes. Suppose some homogeneous system of differential equations has the two solutions x is equal to 2t and y is equal to t squared for t not equal to 0, for example, positive time. What is this system of differential equations equal to? So we already know that the non-time varying or time varying coefficient matrix A is uniquely determined by the fundamental system. And since we know what the general solution of that differential system is, we should be able to reconstruct that particular system of differential equations. So what we have is that our fundamental matrix is going to be equal to the matrix 2t t squared for t not equal to 0. So that means that our Wronskian, w of t, is just going to be equal to 2 times t squared minus t times t, which we see is just 2t squared minus t squared, which is just going to be equal to t squared. And keep in mind, this is not equal to 0 since t is not going to be equal to 0 by assumption. So if that is the case, that means this is indeed our fundamental system of two independent solutions, and moreover, the inverse of this matrix does exist. So it's going to be equal to 1 divided by the determinant of that particular matrix. Then we're going to swap our diagonal entries and then negate the other two. So what we're going to have is the corresponding inverse of our fundamental matrix to be 1 minus 1 over t minus 1 over t and 2 over t squared. So that's the inverse of that matrix. So if that is the case, we also need to find the derivative of our fundamental matrix. So the derivative is just going to be equal to the derivative with respect to time of the variable matrix 2t, t, and t squared, which we know is just going to be equal to 0, 1, 1, and 2t. So once we have these two matrices, then we can reconstruct our system A. So again, A of t is going to be equal to our derivative fundamental matrix times the inverse of our fundamental matrix in that order. Keep in mind, matrices do not necessarily commute. So you're going to have 0, 1, 1, 2t multiplied by 1 minus 1 over t minus 1 over t and then 2 over t squared. So once we multiply these out, what we're going to have is the matrix minus 1 over t, because that 0 just kills off that 1. Then we're going to have 2 over t squared there. Then we're going to have 1 plus minus 2, and then minus 1 over t plus 4 over t, which of course simplifies to minus 1 over t minus 1, 2 over t squared, and 3 over t. So that is our time-varying coefficient matrix, I guess you could say, A. So that means the system of differential equations that has these two solutions in it are x prime of t is equal to minus 1 over t times x plus 2 over t squared times y, and y prime of t is equal to minus 1 times x, and then plus 3 over t y. We can multiply both sides by t squared to make this equation a little bit more nicer to look at. So once we do that, we're just going to have t squared x prime is equal to minus tx plus 2y, and ty prime is equal to minus tx plus 3y. And that is our system of differential equations whose solutions are x is equal to 2t and y is equal to t squared, or any linear combination thereof. So that's pretty nice. So now comes the very important question. How are we going to find our fundamental matrix of solutions for our homogeneous time-varying differential equation? And keep in mind, if you're trying to solve higher order differential equations, this links very easily to those types of problems, such as the Legendre or the Laguerre or the Bessel differential equations where those coefficients are not necessarily constant, right? So you can definitely use this not just to solve systems, but non-constant coefficient linear differential equations. So how are we going to find this phi? So keep in mind our phi satisfies the relation phi prime of t is equal to a of t phi of t, because we already know what a of t is, so we just need to find this matrix phi. But notice that this is just a matrix differential equation. In particular, this is a separable first order matrix ordinary differential equation. So we should be able to find this matrix, or function, I guess you could think of it as, phi. So if that is the case, what we have here, I'm just going to write this in a different way. So d phi dt is going to be equal to a of t times phi of t. And what I'm going to have here is d phi divided by phi of t is equal to a of t dt. Now, some people are going to be uncomfortable with the notation on the left-hand side, but practically all that is, if you want for me to define what this notation means, this is just the same thing as a inverse of t times d phi of t is equal to a of t. dt, right? So this is practically what I am defining. Oh, that should be phi of t, by the way. All right, so if that is the case, then what we can do is just integrate both sides of this equation with respect to phi on the left and t on the right-hand side. And what you're going to have is that phi of t will be equal to e to the integral of a of t dt, which I'm going to notate from here on. The antiderivative of the matrix function a, I'm going to denote that as e fancy a of t, right? So this is our solution. So we know what a is, we know what fancy a is, so as long as we know how to exponentiate a matrix, or exponentiate the antiderivative of a matrix, then that's going to give us a general solution. So let's just take a moment and figure out how we're going to do that. But before we dive into that little linear algebra journey, let's just make sure we understand a couple calculus things. So if script a of t is defined to be equal to the antiderivative of the matrix A of t dt, then if I differentiate script A of t with respect to t, then that's just going to give me the normal time varying matrix A. So this is indeed true. So that's how we can take the derivative of script A. Let's do the derivative of script A squared. So the derivative of script A of t squared, which keep in mind is just the derivative of script A of t times script A of t. Script A is a square matrix, so this is definitely well defined. And then I'm going to be using the product rule here. So what this is this going to be equal to the first times the derivative of the second, and then we're going to have the derivative of the first times the second. Keep in mind, these matrices don't necessarily commute, so make sure you have it in the correct order. So what we have here, because we know that the derivative of script A is A and the derivative of script A is equal to A, so all we have here is script A of t times A of t plus A of t times the script A of t. And if script A and A commute, if this is true, then we can actually simplify this and just write this as 2 script A of t times A of t, if they commute, right? So that gives us an expression for the second derivative of A, and you can of course extend this to the derivative with respect to t of script A of t to some power n, where n is in the set of natural numbers, 2, 3, 4, 5, and higher. So now that we know how to take derivatives of powers of matrices, let's go back to our exponential of that matrix, because our solution, which we're aiming for, which is just this function 5t, which is just going to be equal to e to the script a of t, is going to be equal to what? So if we use the definition of e to the something, that's just powers of that something divided by k factorial. So if that is true, and keep in mind that the derivative of phi of t is equal to just the derivative of e to the a of t, what should this be equal to if we carry this out? What should be equal to a of t times phi of t if phi of t is a solution? So let's see if it is. So the exponential of that matrix A is going to be equal to what? So this is just going to be equal to the derivative with respect to time of, so the one term in the matrix world is just going to be the m by m identity matrix, and then we're going to have script A of t, so that's equal to like x in the Taylor series, and then we're going to have 1 over 2 factorial times script A squared of t, then plus 1 over 3 factorial times script A cubed of t, and so on. So we know that derivatives are linear operators, so we can distribute over addition, and then we're going to take the derivative of each of these matrices. Now, what is the derivative of the identity matrix? Let's just look at the 2 by 2 just to look at that. So the derivative of 1 is just going to be equal to 0, so we're just going to have 0, 0, 0, 0. And when we add the m by m 0 matrix to any of these other matrices, we just get those matrices. So this derivative of the identity matrix just vanishes. So what we're going to have is we're going to have the derivative of script a of t, which we know to be equal to a of t. And then we're going to have the derivative of 1 over 2 factorial times something squared. The 2 comes down, so it cancels with the 2 factorial. And we're going to have that's just going to be equal to script a of t times the derivative of script a, which is just going to be a of t. And then we're going to have 1 over 2 factorial times script a of t squared times a of t. And then we're going to have plus 1 over 3 factorial script a of t cubed times a of t plus and so on. So we're just using some chain rules there that we've already proven before. Now notice that each and every one of these terms has an a in them, so we can factor them out. And keep in mind, we're assuming that a and script a do commute, else this is not necessarily true. So once we have that, that's just going to be equal to a of t times I plus, so we're going to have script a of t there, and then 1 over 2 factorial times script a squared of t plus 1 over 3 factorial times script a cubed of t plus and so on. But this is just the exponential of script a of t, so we're just going to be left with a of t times e to the script a of t, but we know that that's already equal to phi. But keep in mind what this equation was equal to. This was the derivative of phi, so that means this is just going to be equal to a of t phi of t. So if this is the case, that means that phi of t is our solution. And that's true if and only if a and script a commute. So isn't that quite nice? Right? Now keep in mind, if you don't know any theory about commuting matrices, A is just an m by n matrix and A is going to be an m by n matrix. So if you can find the eigenvectors of A in script A and you can prove that those eigenspaces are identically equal to each other, then that also implies that these two matrices commute, which is actually a pretty nice result. So let's assume that we have been tasked to solve the following linear time-varying system of differential equations. Some people also abbreviate linear time-varying as just LTV. So we've just been analyzing LTV systems of differential equations. So obviously we have a homogeneous system of differential equations. This is not a coefficient matrix. Let's just call it A of t. This is our matrix X, and this is our matrix X prime. Right? So this is our matrix setup. So this is definitely an LTV because this is not a constant coefficient matrix. So our eigenvalues and eigenvalues will be changing as time changes. Now, first we need to define our A formally. So A of t is going to be equal to our t, 2, 3, and t, which is a symmetric matrix, and you should be able to show that the antiderivative of this matrix, script a of t, is just going to be equal to 1/2 t squared, and then we're going to have 2t, 3t, and 1/2 t squared. It's also important to note that this is a symmetric matrix and this is a symmetric matrix, and there are some theorems associated with symmetric matrices and commutativity between them, but you should be able to check on your own that for all time t in the set of real numbers, that a times a is equal to a times a. So script A equals A script A, i.e. A and script A commute. So if A and script A commutes, then we should be able to use the theory for which we've built and just exponentiate this script A matrix, and that's going to give us our fundamental system of solutions, and hence we'll have our solution to our homogeneous linear time varying system of differential equations. So once we have that, then we have that our solution is just equal to E script A of t, which if we just write out is just the exponential of the matrix 1/2 t squared, 2t, 3t, 1/2 t squared. right? And keep in mind that there is a little invisible constant here, but if you know that 1 is the solution to the differential equation, then any constant multiple are also solutions, so we can just assume that this constant is equal to 1. Just in case you were curious about any constants, for example, in that particular matrix, script A of t. So the next thing that we need to do is we need to be able to take the exponentiation of this matrix. So we're going to be pulling a little theorem from linear algebra because keep in mind that this matrix should have a full eigenvalue decomposition, right? So if we have e to the a, and let's assume that a has an eigenvalue decomposition of u du inverse, then one should be able to easily verify that this is just going to be equal to the matrix U times the exponential of the matrix D times U inverse. Here, that's just our matrix of eigenvectors. That is also our matrix of eigenvectors, but keep in mind that should be an invertible matrix because our solutions should be independent of each other. We're just looking for them, but we don't know what they are. And this is the exponential of the square matrix containing all of our eigenvalues. So keep in mind, if you do not know what the exponentiation of a diagonal matrix is, I'll just do the 2 by 2 case. This is just going to be equal to the 2 by 2 matrix e to the lambda 1, 0, 0, e to the lambda 2. Right? So that's actually very nice. It's also a diagonal matrix, right? So in some sense, this is just the eigenvalue decomposition for our solution or fundamental solution matrix phi, which is actually pretty neat. So we need to find the time-varying eigenvalues of our antiderivative of our time-varying coefficient matrix script A. So to do that, we're going to find the characteristic polynomial for script A of t, which is going to be a function of lambda and also t. So that's just going to be equal to the determinant of a script A of t minus lambda I, in this case a 2 by 2 identity matrix. So that's going to be equal to the determinant of the matrix 1/2 t squared minus lambda, 1/2 t squared minus lambda, 2t, 3t. And this is pretty nice because we are working with a symmetric matrix, so the eigenvalues and eigenvectors are actually not super difficult to find. So that's just going to be equal to 1/2 t squared minus lambda squared minus 6t squared. And we're just going to be setting this equal to 0 to find our time-varying eigenvalues. So that's a nice quadratic equation. You might be able to solve it just by looking at it, but I'll just specify them here just in case you can't. So lambda 1, and let's actually just call it lambda 1 of t, will be equal to 1/2 t squared plus the square root of 6t, and lambda 2 of t will be equal to 1/2 t squared minus the square root of 6t. Right? So those are eigenvalues. So then you're going to plug these lambdas in, right? So lambda t into those equations, and you're going to find an eigenvector that solves that particular equation. Keep in mind you're going to have one free variable there, and you should be able to show with minimal algebra, I guess you could say, that the eigenvector for lambda 1 of t, which is also a function of time, actually, this is actually going to be a constant. It's just going to be c1 times 2 square root of 6, and v2 of t will be equal to c2 times 2 minus square root of 6. So a lot of algebra there, but nothing too scary. So once you have your eigenvalues and eigenvectors, and keep in mind you can scale these however you prefer. If you want them to be unit vectors, that's purely up to you. But our eigenvector matrix U is just going to be equal to 2 square root of 6, and then 2 minus the square root of 6. The determinant of the U we know is not going to be equal to 0 because they should be independent, which in this case is minus 4 square root of 6. This is going to give us the inverse of this matrix is just going to be equal to 1/4, 1/4, 1 over 2 square root of 6, and minus 1 over 2 square root of 6. Right? So U inverse, and those are our lambdas, and make sure we keep them in this right orientation. So that's going to be our 1/1 term, and that's going to be our 2/2 term with zeros in the other two elements of our diagonal matrix D. So once we have that, that means phi of t will be equal to u, and then d, so the exponential of the matrix, 1/2 t squared plus the square root of 6t, and then 1/2 t squared minus the square root of 6t, 0, 0. Show some lines there just to make sure you can see where our elements are. And then we're going to be multiplying that by 1/4, 1/4, 1 over 2 square root of 6, minus 1 over 2 square root of 6. Right, so that's my u, that's my e to the d, and that's my u inverse. Right, so notice that we can exponentiate those elements using that property that I mentioned before. So that's just going to be equal to 2 square root of 6, 2 minus the square root of 6, times the matrix e to the 1/2 t squared. Let's make sure it's in the right position, t squared, and then I'm actually just going to multiply by e to the square root of 6t. So I'm just going to decompose that exponential because I'm going to do so eventually anyway. So it's going to be e to the 1/2 t squared, e to the 1/2 t squared, and then we're going to have times e to the minus square root of 6t, 0, 0, and then this friendly little matrix at the end. Right, so these are our u, d of our solution, u inverse for our solution. And what I'm going to do is I'm going to factor out this e to the 1/2 t squared out of every one of these four, and I'm going to throw that in the front of this expression because that's practically going to make our solution very, very obvious. So we're going to have e to the 1/2 t squared in the front. That's practically a scalar at a particular fixed time. And then we're going to multiply those three remaining matrices. And here, there's quite a bit of algebra, so I don't want to take up super much time. So I'll sure show you what that comes out to. Let's make this pretty neat. I'll put my e in there. I just need to make sure it aligns pretty nicely. So we're going to have 1/2, then we're going to have e to the square root of 6t, and then plus e to the minus square root of 6t on the first term. Then we're going to have 2 over the square root of 6 times 1/2 e to the square root of t minus e to the minus square root of 6t. And then over here we're going to have, what are we going to have? Minus the square root of 6 over 2 minus, or times 1/2, let's do e to the square root of 6t minus e to the minus the square root of 6t. And then over here, what will we have? 1/2 e to the square root of 6t plus e to the minus the square root of 6t. So that's just the product of those three matrices. Definitely a lot of fun and exciting algebra there. So that's our phi of t. Right? Now, why I have written it in this form, those are just hyperbolic trigonometric functions, sinh and cosh. So what we have here is our solution. So that means phi of t will be equal to, how do I want to write this? So e to the 1/2 t squared. Let's write this as cosh of the square root of 6t, and then minus the square root of 6 over 2 times the hyperbolic sine of the square root of 6t. And then we're going to have 2 over the square root of 6 times the hyperbolic sine of the square root of 6t. And lastly, hyperbolic cosine of the square root of 6t. And notice that that matrix is almost symmetric. Right? And that is our fundamental matrix. Right? So therefore, the solutions to this differential equation are going to be as follows. So that means x of t will be equal to c1 e to the 1/2. How do I want to write this? I'm just going to factor out my exponential time. So let's write it as e to the 1/2 t squared times c1 cosh square root of 6t plus 2 over the square root of 6 You could absorb that into a constant, but I'm not going to. So c2, 2 over the square root of 6 times the hyperbolic sine of the square root of 6t. And then we have our solution for y. So that's going to be equal to e to the 1/2 t squared, and then c1 times minus square root of 6 over 2 times the hyperbolic sine of the square root of 6t, and then plus our c2 hyperbolic cosine of the square root of 6t. And if you were to give a particular solution for x and y at some time bigger than 0, then you should be able to find what those c1s and c2s are. Right? So we clearly see that as t goes to infinity, we know hyperbolic cosine goes to infinity, that goes to infinity too, that goes to infinity too. So as time goes to infinity, x and y are definitely going to grow without bounds. And as t goes to minus infinity, we know that hyperbolic cosine and sine will still go to infinity, but this particular term is going to go to infinity as well, right? Because t squared is still going to be a positive infinite quantity as t goes to minus infinity. And when t is equal to 0, I'll leave it to you to figure out what x and y are going to be equal to at time t is equal to 0. But that's the fundamental ways of analyzing linear time-varying differential equations. That obviously sets you up for how to solve inhomogeneous. All you have to do is just find that particular via variation of parameters, but that's practically the theory. So until next time, where we actually go through some analysis of the behavior of these solutions and a couple special nonlinear systems of differential equations, I did hope you enjoyed this video, and I'll see you in the next ones. Take care.